Good afternoon, everyone. I think that the screen sharing issue is now sorted out. Let other people also join. Only 6 people has joined. Please ask your friends to join quickly. Time was 3:30 and it's 3:32 now. Okay, let me start what we are doing. Okay, so in the morning, so I'll briefly review what we were doing or what we have started basically, right? So just give me 1 minute. Let me start the recording also. Yeah, it's being recorded. Good. Okay, so I'll quickly review. I'm not going to spend much of the time on what we had done in the last lecture. So we were basically looking at how we can calculate the entropy of mixing, right? By mixing, I mean to say is that if I have two different samples of two gases, then if I mix them, then what would be the change in entropy for that particular situation will be. So that was what we were talking about in last lecture. So then as I explained then also that my entropy is basically is an extensive parameter, right? So what I mean to say by that is that if you scale up your extensive parameter or like energy or number of particles or volume, then entropy is expected to scale up with the same factor alpha. But that doesn't happen if we just focus on this expression we derived earlier by considering this number of microstates laying between energy interval E plus minus delta by 2, right? So this we derived or just learned in the last lecture. So now the idea is that yeah, this is whatever I'm saying, and this situation is basically termed as a Gibbs paradox in literature, and we have to see that how we can go about it. So just to have a bit deeper understanding of that, I mean to say that this doesn't scale up. So I started one discussion. I'll review that quickly again. And so situation was like this. We consider two different gases. Important term here is different. So they are different. Different mean to say the mass of the particles, so M1, M2, they are different, right? So yeah, that's only essentially what different mean to say is, right? Although you can also have a different densities, it means that this N1 by V1 factor kind of thing, so number of particles per unit volume, this is also different for both gases, right? But we'll see in special cases, even if you make these two similar and keep M1 and M2 different, like number density can be made same, but particles are basically different so that they have different masses. Even then we are going to get that paradox kind of thing. Okay, so then this is nothing but again writing your entropy expression which we derived in the morning, and this I is basically for system number 1 or 2, right? So we can write initial total entropy just by summing these to the total entropy of system 1 and system 2. Then we also saw this thing that now if I mix these two gases, two different gases, then my total entropy can be written like this, right? So where this summation runs over two indices, first and second, and this V will appear as I explained in the last lecture, that because now my N1 number of particle, this full volume is accessible to these particles, so that's why this V appear instead of V1. Rest everything is same, nothing is going to change in expression for S1 for example. Only change is this V. Okay, so similarly my N2 will have access to full volume now. So N2 number of particles of sample 2 gas that will have full access to this full volume. So that's why N2 term will also appear, and this is nothing new. Only trick is here, right? So now we can easily calculate what is the entropy of mixing for such a situation. That's how just you can say the final minus initial kind of thing. So final is this total entropy is written here, and initial was just a sum of the entropies, right? So and we just saw, and if you use these expression given by equation number 1 and equation number 2, to come up with this expression. So this expression look like this, the change in entropy, or you can say entropy of mixing. So yeah, so this number comes out to be positive, as it should be for a irreversible process. Irreversible means, as mentioned last time also, that you can't uh, like do a physical process to separate these two gases into their initial situation. So this is not a reversible process basically. Okay, so you can't like pick each individual particle and just separate them out. That's not a physical thing. Okay, so this process is irreversible, and every irreversible process accompanied by a increase in entropy. That's what this is saying here. Now let's go into a bit a very specialized cases. So now I'm putting this special condition that two gas samples which I'm considering in this, you can say, a situation, they both have same particle density. So it means now hope you understand, right? This we wrote earlier also, that this n is my particle density, that n by v. It also appear in this ideal gas equation where we had pv is equal to small n rt kind of thing, right? So this kind of thing was there. So this particle density is same for both of them. So then I can update my this expression, because now I can very easily write my v, which is appearing here, which is v1 plus v2 divided by v1. It is equally can be written as n1 plus n2 divided by n1. So this is equally good, right? Because if you take v1 there and this n1 plus n2 here, it is just this condition, right? So we can write the this change in entropy in terms of particle numbers like this, right? And this star over this change in entropy is basically this star, right? This, because we are considering a special case. This is not a general change in entropy expression. General will look something like this. This is the general one. Even if you don't have particle density same, even then this is valid, right? But this particular expression is only valid if particle densities are same. So that's the meaning of this star here. Okay, so this is again positive. Nonetheless, it is very clear to see from here that this is also a positive, which is again as expected. There is still no problem till now, because even this process is irreversible. Although particle densities are same, but gases are still different, right? So your m1 and m2, they are not same. So that's why this has to be positive. That's fine. So the weird situation is going to come ahead. So let me show you that thing to you. Now you see that even if you make these m1 and m2 same, now try to understand this point. Okay, this is really very critical one, and this is the point where here this Gibbs paradox comes into like picture, why this situation is so paradoxical. Okay, so even if I make these m1 and m2 same, now my s total will be written like this. This is, I would say, let me show you the expression for s total. Mm, it's here, right? So now you see, for first number of particle I will have n1 here and n1 here, right? So I will have expression like this. Let me write this part somewhere. So my s total, I'll write it here. It was summation ni k, and let me just see it from here, n1k log of my volume, where it is here. So it's log of v plus 3 by 2 nik, and then we have some terms raised to power 3, but let me see that, because I don't want to make mistakes. So okay, it's not exactly like this. Okay, say 3 by 2 nik, in the bracket I have, okay, I hope I can write that here. It's 1 plus, it's 2 pi mi k K is this Boltzmann constant, so that's small k I'm using for most of the time, by h square, this whole thing raised to power 3 by 2. So this is the expression. Now what I have done is, of course, this is running over both the gases, number 1 and number 2. Okay, so now this mi is same because I took identical, like same gases on in both the compartments. So this mi, I mean to say m1 is equals to m2 is equals to m basically, right? So if I now try to write this thing, this would look something like this: n1, so k, I'm just opening this summation just for your clarity. Log V plus 3 by 2 N1 K, and in the bracket I will have 1 plus 2 pi M. So this M is same for both of them. So M1 is just M because both are same gases essentially. KT, and we also took temperature to be same, divided by h square, that's the Planck's constant, raised to power 3 by 2, bracket close. Now next term would be a plus n2, right? And again k log v plus 3 by 2 n2 k, and in the bracket nothing will change. Now you see you can club these two terms because rest everything is same. So how it will look like? So I will have a n1 plus n2 k log v. So I will have a term like here. So it's n k log v, because n1 plus n2 is just n, total number of gas molecules or atoms, what you would say if you like that. So it's 3 by 2. Similarly, this n1 plus n2 be written as total n, and of course k, and in the bracket you have same term. So this is your total entropy. Okay, and yes, and if you try to write entropy of individual gases, so they will look something like this. S1 would have this form, so it will be n1 k log v1 only. Mind it, it's not v now because you are talking about only the entropy of gas sample 1. So it's only occupying volume v1 before mixing. So then plus 3 by 2 n1 k, and in the bracket nothing is going to change, so this bracket will remain same, right? So it's still m. Similarly you can write for s2, so that is now your n2 k log v2 plus 3 by 2 n2. Now k, because we are talking about second gas sample, although both gases have same nature, they are same gases at same particle density, same mass for each individual atom or molecule, right? So now if I look for this delta s, which is nothing but s total minus s1 plus s2, so this is my change in entropy. Okay, and this expression I calculated, which is written here, no, here. Okay, so this s total is as I explained on above slide. So this delta s is again coming out to be positive. Okay, you can calculate this thing, this is not hard to calculate. So few terms will get cancelled out and a few terms will remain there. But if you try to calculate this s for this special case number 2, which I'm considering here, right, the delta s is again coming out to be positive. This is a contradictory situation, right? Why contradictory? Let me explain this one. Okay, so let me take a blank sheet. Okay, here now imagine we had two boxes, right? So I'll just make a two-dimensional case. Okay, let me not draw it here, let it be here. Okay, so here this is my gas sample number 1, this is my gas sample number 2, right? This guy had n1 number of particle and volume was v1. This gas had n2 number of particle and volume was v2, and of course v1 was not equal to v2, that's why I made this asymmetrical, right? And of course this plus is equals to total volume, and this plus is equals to total number of gas molecules or atoms. Okay, and we assumed that n1 upon v1 equals to n2 upon v2 equals to n1 plus n2 divided by v1 plus v2. This was my special case number 2. Okay, now my gas, both samples are of same gas basically. Okay, so what I have done is I removed this partition, right? So what do you think is going to change? Of course, molecules are going to go here and there. There is no doubt about that. But do you think density is going to change? Because even initially they both had same density. So although there can be a movement, right? But there is no net change in the number of particles is going to happen because density was same on both the sides, right? And now suppose how I can revert this process. So suppose I put this partition back here. So I'll reach up to the initial condition where I have started from. Because if a gas atom or molecule moved from this place to there and there is no net change, you can't identify because we are not tracking each and individual atoms and molecules. We are concerned with the numbers now. We are not interested in individual atoms, and of course those are not distinguishable one, right? So they are indistinguishable. So the idea is if I so essentially I brought my system to initial conditions, so there should be no net change. This delta S should be zero in this scenario when both of my samples are essentially same gas actually. Okay, so, but if I look at this situation which we derived here, my delta S comes out to be positive. Okay, but the problem with this is it means that then what's the problem basically? The problem is basically whatever we have started with, that S as K log tau, it means there must be some problem with this guy, right? So this entropy expression for this ideal gas is not correct. So this situation that this should not happen for a gas sample of same gas in two compartments. That's basically highlighting the kind of paradox which we uh, term as Gibbs paradox, right? So how we can go about it, or what Gibbs basically proposed, that's something that goes something like this. And before moving ahead, if you have any question, please tell me. You can unmute and you can ask questions. I'll wait for maybe 30 seconds so that you can make up your mind. This is really critical, let me tell you. Okay, and even the remedy to this Gibbs paradox as proposed by Gibbs, it is kind of ad hoc, and whatever explanation we are going to see, that is also kind of ad hoc, but we'll see when we will shift to quantum statistical mechanics that what's the fundamental reason for this ad hoc remedies. Okay, so you may not appreciate that right now, but I'll try to give you or explain that why or how we are going to solve this problem. Okay, although I gave a hint in the beginning that how we can solve this is something like this. Let me show you. So this was when we started this. If you remember, this was the expression of this, although this is looking okay. Let me clean this up a little bit. No, I know it's a bit patient testing, but that's okay. So what my idea is, we started with this expression for entropy, which we like derived after a lot of hard work. Okay, so the argument what I gave, or this all these special cases had in common, is that they depend upon this entropy expression, right? So if they depend upon this, as I said, as required by the extensive parameter definition, if I scale up my energies or number of particles, right, and volume, so my entropy should also scale up. That's the requirement, right? So it is written here in terms of these mathematical symbols, but this expression doesn't do so. That's what we observed, that for example, for a two gas samples of same gas with same particle density, if I remove this wall, then they are going to mix. Then I put this wall back, essentially nothing has happened. You can't identify the difference between that whether they have mixed or not. So it means this delta S should come out to be zero, but this expression doesn't ensure that. Okay, so quick thing I which I told you in the morning also, that if this n goes to alpha n, and actually this e by n take care of each other. So if e goes to alpha e, n goes to alpha n, this as a whole not going to change, but this v goes to alpha v. So of course this n also goes to alpha n, because alpha is that kind of scaling. So this s doesn't go to alphas, which is required as per definition of the extensive parameter, entropy being extensive parameter. It doesn't happen. Why? Because this alpha you can't take out of this whole expression, whole log, right? So if I put some n kind of thing here, okay, so then if this n goes to alpha, now this alpha will go away. Then this can be this can represent expression for entropy, which essentially are extensive parameter, right? But we can't do it like this, that okay, put n, now it's correct, right? There must be some justification for that. Okay, and essentially something similar what Gibbs had done with this entropy expression to avoid this paradoxical situation. That's what we generally term as Gibbs remedy to Gibbs paradox. Okay, so what they have done is basically, so they just did, or Gibbs, what he did, he said that, yeah, this I just told you how to calculate, because we wrote expression for S total when I was talking about same gas in both the compartments with identical particle density at same temperatures. So these all these expression I wrote are here, right? So these all expressions are there, and you can calculate this delta S star also. Okay. So what he proposed is, and this can be shown to be like coming out to be like this. He said that if we diminish S by this number, actually he was saying that we diminish this number of microstate by n factorial, actually meaning to say same, diminish S by k log n factorial, because you know that if you want to reach up to entropy, you have to just take the k times log of this guy, right? So diminish this by n factorial number of microstates, and diminish S1 by k log n1 and S2 by k log n2 in such a way that this total entropy get diminished by k log n plus n2 factorial. If we do this, if we change bring about these ad hoc solutions, okay, so if you remember, yeah, I'll come to that later. So then your delta S will approach zero instead of giving this non-zero answer. This is not zero, okay, this is positive. But if we diminish all these things, all these entropies as proposed here, then we can achieve this thing which is basically demanded. Okay, so why we are doing this, or why we will diminish this thing, I'll try to explain this with the help of one example. Let's see if we can work out that. Just yeah, this is what he they said. Okay, just let me see if I just give me a sec. This is nothing but if we propose that, this is what I said, basically diminish your number of microstates by n factorial, or be it a sigma or be it a tau, both has to be diminished by this number, then we can avoid that problem, right? So first let me tell you, if we do this, if we diminish the number of microstate, I mean to say, if I just take this tau which we derived earlier at the beginning of lecture, if I just diminish this by n factorial, divide this number by n factorial, then my entropy expression which was written here, this one, it will get modified. And how it will look like, so that I just wrote here. First, let's assume that this proposal is correct, and how this is going to modify our things, let's see that. So then my entropy expression is going to change like this, right? So at that, instead of that 3 by 5 3 by 2 term, I will have now a 5 by 2 term. One additional term will come out to due to this factorial, n factorial, right? Or you can modify this, just give me 1 minute. Okay, sorry for the interruption. Okay, let's go back to this thing. Okay, so this is if I like agree upon that we need to diminish all the microstates by respective number of particles involved factorial. The reason we will see soon. So then my entropy expression is going to upgrade like this. This is not very hard to see. Okay, so yeah, so this I'm also referring to equation number 21 on page 20. This will get modified. This same equation which we wrote at the starting of this article. Okay, and this can be rearranged like this also. So basically what I have done is now if you see that n came here. Okay, so this e by n is going to take care of the fact that even if I multiply this by alpha and this by alpha, this is not going to change. And this n which is appearing here due to division by this n factorial, now if v goes to v alpha v and n goes to alpha n, this v by n ratio is not going to change. This is basically reciprocal of the particle density. Okay, but there are certain more you can say changes brought about by this n factorial division. So that 3 by 2 factor changed to now 5 by 2, and rest less or more everything is same. Okay, so now this can be modified like this also. You can take this v by n term separately, then this h cube you can bring in, so that it will become h square because there is a 3 by 2 there, and e again you can feed in as that 3 by 2 n kt kind of thing. So then you will have this kt stuck here, and this 5 by 3 is just you can say taking this 5 by 3 common, 3 by 2 here, and 3 by 2 is coming from this power also, right? So this is just a rearrangement. I think you can do this. I mean, it's not very hard. Okay, now this is going to solve this issue as I just mentioned. And this equation had a certain name in literature also. It's called a Sacco-Tetrod equation, right? The scientists basically modified this equation or put this equation in this particular form, named after them. And this equation can be, again, as usual, we do it so many times, that this equation can be inverted for energy also, right? It's here. So nothing new in this, no physics at all. Okay, so now why I'm writing, because I told you this thing many time, so that if in principle you can write your s as a function of macrostate n, v and e, or you can invert this equation to write your energy as a function of n, v and s, then whole of the thermodynamics is going to follow. Okay, you might remember this let me show you just for your sake that how we can do this. Yeah, this kind of things, right? So your CV is going to be curly by curly t at constant n, p is going to be derived like this, then you can derive this equation cp. So all of these things are going to be easily doable if you have your energy as a function of a temperature, volume, number of particles kind of thing, right? So that's what we have done here. So although that's not the motive to do. So now why there is a n factorial kind of thing. Okay, so let me now go into bit detail, and this is also termed as a couple of paragraphs written at the end of this chapter. They call it the correct enumeration of the number of microstates. So what's the meaning of Gibbs remedy, right? So they said, okay, so instead of tau, you take not tau but tau by n factorial, or tau1 divided by n1 factorial. So where tau1 is the entropy or number of microstate accessible to system number 1, where your S1 was k log tau1. So instead of this, now I will have n1 factorial here. Okay, similarly, entropy of the system, I will be having k log original tau we calculated, but now we are diminishing that by n factorial. Why we are doing this? This was done by Gibbs, but what is the meaning of this thing? Okay, the idea was I'll give you this example. Okay, so this is, you are distributing 4 particles in 2 compartments. This is one example which you did in your graduation class BSc when you just started your thermodynamics and statistical mechanics chapter. So basically, if you are having 4 particles distributing amongst 2 compartments, right? Let me look at this macrostate 3-1. 3-1 means 3 particles are going into one box, and 1 particle is going into another compartment or box. I will be calling these names interchangeably. Okay, so kindly bear with that. So the option is something like this. You can put your one particle here and all other three particle here, right? And another microstate could be, you can put B particle here and ACD here, or you can put one particle. So this is basically your compartment number one, this is compartment number two, or box number one or two, right? So these are, I'm just looking at the permutation what I can have with this macrostate. So this is basically my macrostate, right? For this distribution, it's not, we are not doing defining macrostate like this NVE, although this is something similar, right? Because n is 4 here. I talked about this volume is basically the total volume of these two compartments, and E energy is if I assign some energy eigenvalues to these two boxes, then that can define my E also, right? In fact, this is similar specification. So if I have C in compartment number 2, then of course A, B and D will go there, and fourth could be D in compartment or box number 2, and A, B, C comes here. So these are 4 configurations, right? And for this macrostate, there is something called thermodynamical probability of this macrostate, and that is nothing but it is given by NC N1, where N is the total number of particles and N1 are the number of particles going in one particular compartment. This is also equal to NC2. That's not hard to see. And N1 plus N2 is total number of particles. And this, for this particular scenario, comes out to be 4. You can calculate that 4C3 equals to 4C1 is equals to 4. That's what the number of microstate in this macrostate is. So this is all good, very well, like adjustable thing, absorbable thing, I should say. Okay, but the problem with this configuration is this, that our particle, our gas atoms or our gas molecules, they are not being labeled, right? How I can do this? Suppose I have two balls, for example. I have two different balls. Okay, I put one atom of a hydrogen atom in this bowl, and I have another hydrogen atom, and I put that hydrogen atom in this bowl. Okay, and you saw all this happening. And now what I do is I just ask you to close your eyes. Then I choose either of two options, which are as follows. Either I keep these two atoms in their respective bowl, number 1 or 2. I can label bowl, that's not a problem. Okay, or I can interchange them. I have done either of these two things. Then I ask you to open your eyes. So can you tell me that whether I interchange them or not? Can anybody comment and tell me that? Can you tell me? I think this is very easy thing to understand. You can't tell me because these two are identical. There is nothing, no property attached to them which can distinguish them. So they are basically indistinguishable in nature, right? So that's the problem with the counting the number of microstate, because when we were doing this calculation to compute this number, the number of microstate for a given macrostate NVE, we basically treated our particles as labeled, that all these, like in this, in computing this number, all these 4 states were distinct, but actually they are not. So what I essentially I have is, I have 4 identical balls. So what I can do is I can put these 3 balls here and 1 ball here. That's all. So it doesn't matter which ball is like placed where. All these 4 microstates are essentially same. Actually, each macrostate corresponds to only one microstate if my particles are indistinguishable. There is no much further detail to this. Okay, so how to get rid of this thing? There is one thing, how you calculated your this thermodynamical probability in your lower class. It was something like this. So these are basically number of different microstates accessible for a given macrostate n1 and 2. So this was basically was like this. It was n factorial by n1 factorial into n2 factorial. Basically, these are the total possible number of ways in which these n1 and 2 particles can rearrange themselves into these two compartments. So this is, these n factorial is that those total number of ways, and this is multiplied. This is basically, actually it came like this. So n factorial is n1 n2 times n1 factorial times n2 factorials. But these permutations are meaningless. Why they are meaningless? But basically this number is saying how n1 particles are arranging themselves in box number 1. It doesn't matter, right? How these three are arranging themselves within this box, that is not good. These are, that's why they are called meaningless. So I am basically interested in this number. Okay, so these are basically meaningful as long as these particles are distinguishable. So these are meaningful number of ways. So that's how this number was calculated basically. But problem with this is, even if they are not labeled, then I have to get rid of this number. So that's why instead of for this weight factor, they divided this whole number by n factorial, because they all mean same. So that's why and your this total number of I would say microstates accessible to the system, they have been divided by total number of particle factorial, right? So this is kind of a very simple explanation that why it has been done like this, to avoid what we call as Gibbs paradox. Okay, yeah, this is example I'm taking, same what I have discussed right here. Okay, and you would see that, let me move ahead a bit. So yeah, so I'm saying that these all permutations are correct only if particles are distinguishable, and if you can't distinguish, then you can't put a label upon them, then this has to be reduced by some factor. But it's not an easy task actually to tell that how this is going to be done. And this set, what do you mean by this set ni set means that you put n1 number of particle in first state or first level, n2 number of particles in second, n3 in third, n4 in fourth, and so on, in such a way that this summation ni is equal to total n is going to be satisfied. And also there is another constraint, if you remember, that ni and this epsilon i, where epsilon I are the energies where you put these particles, E2, E3, E4, and so on. This has to sum to the total energy of the macrostate, the way it was defined. Okay, so, and now what I mean to say, what I have explained here with the example of this four particle in two boxes, translate to this situation would be that if you put n1 number of particles in E1 state and n2 number of particles in E2 state. Let me take very specific example, that uh, suppose I have n1 as 2 and n2 as 3. So I put two particles in E1 state and I put three particles in E2 state. So actually these two particles and these three particles, they are identical, they are not distinguishable. So it doesn't matter if I take these two particles there, and out of these three I put two particles back here, and these two make now new three. These two different configuration, if they were distinguishable, were different, but now they both mean same, right? So that's why instead of talking about these number of permutations, I have to divide this, to diminish this number by n factorial. That's again and again actually I'm giving you same expression. So just to accommodate this indistinguishability, so I have to get rid of this number of permutation. I have to jump to this thing to update my this weight factor, right? And that's why this n factorial division has been done in the calculation of this number of microstate calculation, right? So I think you can appreciate this, and even you can see if my n is very large, this is going to be a very low number. And ideally saying, this weight should either reach a unity, or it should actually vanish. Like it is supposed to take either 1 or 0, and we'll see when we'll be talking in quantum statistics, uh, for example Fermi-Dirac statistic kind of thing, they will in fact either will take value 1 or 0. I would just wind up this thing by saying a couple of things only. So what I mean to say is, yeah, that's what in quantum statistics we will see this, right? I am not assuming that you from just now that you like understand that how why this is going to be 1 or 0. So you will see that this is going to take either of these values, right? So but if instead of this distribution, if we go to classical limit, what classical limit I mean to say is that temperature is very high and the particle density is very low. I mentioned this earlier also. So high temperature means the higher number of energy states are now accessible for my system. Okay, and then there are the chances that most of the time these levels are empty. Okay, these levels, and there are occasionally that some of these levels are being occupied. So a particle can occupy one of the particle is going somewhere, and rarely it may will happen that two particles are occupying same level. Okay, so this is what I mean to say by classical limit. So this Ni, which I will be terming as the occupation number of a particular energy level, it is going to following this general trend, what we call the classical limit. Okay, and of course, as I said earlier, this permutations need to be replaced by this number dividing this by n factorial in order to avoid what we call as Gibbs paradox. This whole discussion is not that much deeper, or I would say it is not that much satisfactory answer that why this n factorial is being used to diminish the number of microstate accessible to a macrostate NVE. It will get more you will get a more clear picture when we are going to jump into quantum statistics. Actually, then you will have a deeper understanding, and this indistinguishability, this is going to play a major role when we will be dealing with the quantum statistics, right? So I think with this I will wind up today's discussion, and I will request you to please read up the book, right? This is a quite time consuming to understand the arguments of what is going on, right? And we can review this again, hopefully with your questions in next lecture, right? And right now, even if you have some question you may ask, and otherwise I think you are good to leave the session. Thank you.